Hello everyone, my name is Dr. Subir Roy. This is the submission for the peer graded assignment for the course project. Uh, this is towards the course Managing Machine Learning Projects by Duke University. Let me begin with my project. It's known as Finding FABRY. Let me come to the problem. The problem statement here is, can we use artificial intelligence to diagnose Fabry disease using electrocardiogram or ECG? Now, diagnosing Fabry disease using ECG is actually a very attractive opportunity for machine learning based solution. Diagnosis of Fabry disease is extremely challenging for human experts. Currently, diagnosis of Fabry disease is very difficult for a physician due to various number of factors. This challenge leads to delay in diagnosis by 20 to 50 years for majority of the patients. In fact, majority of the patients do not get diagnosed at all. Artificial intelligence can pick up patterns and learn, which might be impossible even for a well-trained human eye. All the patients who suffer from Fabry disease have changes in the heart that can be picked up by ECG. Unfortunately, it is extremely difficult even for a trained human eye to identify these ECG patterns that can suggest diagnosis of Fabry disease. Now, let's talk about the CRISP-DM process in terms of business understanding when we are trying to define the problem. For this problem, the target users are cardiologists, nephrologists, and neurologists. The problem we are trying to solve is how to automate diagnosis of Fabry disease just by scanning ECG of a patient. Now, let's understand the current process for diagnosis of Fabry disease and the gaps in that particular process. Currently, diagnosis of Fabry disease is highly challenging, as we saw. Even with detailed clinical examination and multiple tests, most patients suffering from this disease do not get diagnosed for several decades. It takes a combination of extremely high level of knowledge, very high degree of clinical suspicion, and then confirming that using enzymatic evaluations and genetic tests, finally to arrive at the diagnosis. Thus, the current way of diagnosing Fabry disease is highly inefficient and extremely time consuming. Delay in diagnosis mortally impacts these patients. The damages occurring in heart, brain, and kidneys eventually become irreversible with time, and hence early diagnosis is absolutely critical so that one can treat these patients earlier and more effectively. Now, from the CRISP-DM perspective, how do we define the success metrics? In terms of outcome metrics, we would like to see 4 times increase in the diagnosis of Fabry disease using this solution. And in terms of output matrix, we want to use precision recall curve. And that is purely because of very high level of class imbalance in terms of data. You will have majority of the patients with no diagnosis of Fabry disease and a very minority of the patients who actually have Fabry disease. The other output metric we would like to use is the ROC curve. Now, what are the potential relevant factors which can be used for correlation, which can be used as the labels? We have identified 8 important labels: the P-wave duration as per the ECG, QT interval, PQ interval. From clinical perspective, glomerular filtration rate, history of stroke, history of renal failure, left ventricular mass, and from demographic perspective, gender. We believe that these 8 factors have got very high correlation in terms of diagnosis of Fabry disease. Now let's talk about the solution validation plan. What is the concept solution? The proposed solution concept is an AI sourced code that will be used to integrate into ECG machines. Currently, ECG machines run a code that can read ECGs and automatically tell if there is an abnormality in the axis or the voltage. With this new inserted AI code, the ECG machine will red flag the ECG reading with a note of suspected Fabry disease in case the correlations are significant. This red flag will then trigger the physician to conduct genetic and enzymatic analysis, which will either confirm or rule out diagnosis of Fabry disease. And this confirmation will be fed into the UI of the machine, thus allowing the AI algorithm to retrain itself, thus improving the predictive power each time. Now, how do we validate this concept solution? We will create a model concept based on heuristics and insert the corresponding heuristic code on ECG machines at few cardiology clinics. We will then evaluate how easy and intuitive the process is and collect feedback from the users to improve any part of this entire process or the UI. We will version each iteration and seek feedback from internal experts such as the data scientists and the machine learning engineers to evaluate the feasibility of the new or altered features which are being proposed by the users. The final version, which gives the best response from the user and which are deemed feasible by the internal experts, will be the end design. That will be finally the aim in terms of building the final model. Now let's talk about the machine learning system design in terms of the approach, whether it will be cloud AI or edge AI, whether the learning will be offline, or whether the predictions will be online or batch. Now, Fabry disease is a rare disease. Very, very few patients. The current prevalence is hardly around 1 in 40,000. So we will use hybrid approach and combine both AI, cloud AI and edge AI. This will enable quick diagnosis at the user end while ensuring complete leverage of the cloud-based AI. Since the cloud AI will retrain using the user feedback. So users are going to tell whether the AI predicted diagnosis is true or false based on genetic testing. This hybrid approach is absolutely critical. The data points necessary for learning and retraining would actually be extremely limited at the edge interface because it's a rare diagnosis. There are very few patients who are really having Fabry disease and then coming to the clinic. And hence, the learning has to be online. And due to similar reasons, the predictions also should be online rather than batch-based so that the entire AI infrastructure can benefit from the data generated along with the feedback and continuously improve despite limited data sets. So to summarize, we are using hybrid approach, combining both cloud AI and edge AI. The learning would be online and the predictions would be online. Now, what are the potential risks in the production? There are two which we have identified. The first is inefficiency due to limited initial data. As we saw, it's a rare disease. So one source of issue can be because of limited initial data. There will be very, very limited data on which the model will be trained and then launched. This itself will lead to an inefficient model at the start, but we envisage a continuously self-training model. This self-training will allow the inefficiency to, over a period of time, average out, and this will keep on improving as more and more patients keep flowing into the system. The other issue or risk, what we have identified, is a potential concept drift. As the diagnosis improves and the patients start getting treated, the treatment itself might change the ECG parameters linked to Fabry disease, leading to substantial concept drift. Remember, we had identified a few features like the P wave duration, the QT interval, etc., which are linked to Fabry disease. But this linking has been identified in patients who are untreated. What happens when the patient is treated? Will these correlations change? Maybe, may not be, we do not know. But technically, there is a risk that there will be a concept drift once a large set of patients start getting treated. However, this part will get resolved by putting treatment label, treatment status and duration of treatment as labels and retrain the machine learning algorithm once we have substantial data on these treated patients as well. So that's it from my end. I hope you liked my project, and I hope that I was able to answer all the questions asked in the project. Looking forward for your feedback. Thank you.